So we learned that weight is equal to force of weight, is equal to mass times gravity. It's the mass of the object we're interested in times gravitational acceleration. On Earth, this has a very, very specific value. It's 9.8 meters per second squared. On the Moon, it's going to have different values, like 1.62 meters per second squared. Or Jupiter is going to be like 19 meters per second squared. So we're looking at our instructor. He has a mass of 77.2 kilograms. We want to know his weight. Well, we found that. That force of weight is equal to the 77.2 kilograms times the 9.8 meters per second squared gives us a very specific value. Right? That gives us 756.56. When we round to sig figs, it's going to be 757. And that's in Newton. So that is his weight. If we now look at the same instructor, but he's standing still, and we want to know the normal force from the floor acting on the instructor, we need to talk about the free body diagram. He has his weight down and the normal force, which is up. After you draw your free body diagram, the first thing that you should do is apply Newton's second law, which tells you the sum of the forces is equal to the mass times the acceleration. We're dealing in the y direction because it's up and down, so the sum of my forces in the y direction is equal to the mass of my object times the acceleration in the y direction. Because he's standing still, he has no acceleration. This term goes to 0, so my whole right-hand side is 0. Right? Now we're going to replace the sum of the forces with the actual sum of the forces. Any forces which are up will be positive, any forces which are down will be negative. So my normal force, which is up, is positive. So plus normal force plus my force of weight, which is down, which is negative, is equal to 0. I could also write this as normal force minus force of weight is equal to 0. We're specifically looking for the normal force, so when we rearrange our equation for that, we see the fact that my normal force is equal to the force of my weight. Well, we just found that because it's the same instructor. So my normal force in this particular case is going to be 757 newtons. Now the problem changes a little bit when you add in the element of acceleration. So he's jumping, he's applying a force to the floor. That force is accelerating him upward so he can jump. We're talking about him actually being in contact with the floor. It's the process of jumping. So we're still looking at the same sort of problem here, but now his normal force is going to be larger than his weight because that's sort of what's driving him upwards. We do have an upward acceleration. We're going to do the same thing we did before. The sum of the forces acting on my object is equal to the mass of my object times its acceleration, but we can no longer cancel this term out. That has to stay. We're going to replace the other side of my equation with my normal force and force of weight. This force up, this force down. All right, and we are specifically interested in what is the value of the normal force. But when I do that, I'm rearranging this equation so that my normal force is by itself. Normal force is equal to the force of weight plus the mass times acceleration. We can, in this particular case, use the force of weight from above, or we can substitute in the fact that we know that force of weight is equal to mass times gravity. Please ignore my cat crying in the background. I do this because you're going to see this sort of formula before. You're not given this. This is not necessarily something to memorize, but this is a process you're going to see, especially if you're doing anything on Khan Academy. So when I rearrange this, I get my normal force is equal to the mass times my gravity plus my acceleration. So this is the most simplified version of this equation. We can now go ahead and sort of plug and chug our information. So normal is equal to that 77.2 kilograms times the 9.8 meters per second squared plus the 13 meters per second squared. And we can plug all this into our calculator. And we get the fact that the normal force from the floor is equal to 1,760 newtons. So a lot of force. He gets a lot more force from the floor than he did before once he pushes down on it. All right, hope that helps.